back to our channel. So in today's session we'll discuss about one more topic in automata theory, that is equivalence of two finite state machines. So in the previous sessions we have seen how to construct the DFA, how to construct the NFA, and how to convert the NFA with epsilon to without epsilon, and how can we convert the NFA to DFA and all these things. And now we'll go with the equivalence. So we need to check the equivalence of two finite state machines, right? So equivalence between two finite state machines. So for this we will consider two finite state machines and we'll check whether both are equal or not. So first finite state machine, I am taking this one, so Q0, and go with the Q1, which is a final state, which is having the self transitions for 0 and 1, and again from here it is 1. So you can see this is a one finite state machine, so two states, and every state is having a transition over every input symbol 0 and 1. Again, let us take one more example because we need to compare the two things, right? So here I am taking the states as P0, P1, P2 in order to avoid the confusion. So P0 on 1 it moves to P1, P1 on 1 it moves to P2, which is a final state. Sorry, P1 will be the final state, and here P2, and give the self transitions here over zeros, and I will give the transition for 1, right? So these are the two finite state machines, and here you can see Q0 is having a transition over 0 and 1, Q1 is having a transition over 0 and 1, and P0 is having a transition for 0, 1, P1 is having a transition for 0, 1, P2 is having a transition for 0, 1. Now we need to check whether these two are equal or not. Now just start with the initial states. Right? So 0 and 1, and here you can start with the initial state. What are the initial states here? So here it is a Q0. Okay, here it is a Q0. This is the initial state and this is the initial state. Comma P0. So this forms one state. Okay, this forms one state. So Q0 upon 0 it moves to Q0 itself, and P0 upon 0 it moves to P0 itself. So the same state. Okay, same state. Coming to the 1. Q0 on 1 it moves to Q1. P0 on 1 it moves to P1. Right? So you can observe there is a one more state here. Okay, consider this as a single state. So it forms a new state upon transition 1. So you need to find out the transition for this new state. So again I will follow the new states. Q1, P1. So Q1 on 0 it moves to Q1 itself. P1 on 0 it moves to P1 itself. Right? And the same state. Now again find the transition for over 1, right? Q1 on 1 it moves to Q0, and P1 on 1 it moves to P2. So you can observe this is a one more new state. Okay, another new state appeared. Now we need to find out the transition for this new state. So we need to repeat the same procedure until the new, I mean it doesn't forms a new state. Okay, until it doesn't forms a new state we need to repeat the same procedure. Now this is a new state, so find out the transition over 0 and 1 for this new state. So I am going with this one, Q0 and P2. So simply you can see Q0 upon 0 it moves to Q0. P2 upon 0 it moves to P2, the same state. Okay, now 1. Q0 upon 1 it moves to Q1, and P2 upon 1 it moves to P1. So this is already available state. Okay, this is already available state. So you can see there is no new state formed here. So we can stop the procedure and now check each and every pair whether it consists of either both the initial states, I mean non-final states, or both are final states. So it doesn't contain the combination of final state and non-final state. If the pair contains the final state and non-final state, that implies these two finite state machines are not equal. So you can observe here Q0 and P0. Here in the first diagram Q0 is in initial state and P0 is initial state. So forget about the initial state also. We have to find whether they are the non-final states or final states. So Q0 is non-final state, P0 is non-final state. So this is a combination of non-final states, right? Q1, P1. Q1 is a final state, P1 is a final state. So this is, both are in final states, right? Q1, P1, again, both are final states. Q0, P2. Q0 is a non-final state, P2 is non-final state. Yes, right. So it should not contain a final state and non-final state, right? So Q0 and P2, again, it is a non-final state. Q1 and P1, it is a final state. So you can see, any one of the pair doesn't have the combination of final state and non-final state. This implies both are equal. Both the finite state machines are equal. So just trace it. So here you can find two states. Here you can find the three states. Just minimize the DFA. So we have already discussed about this minimization of DFA in the previous session, and I will post the link in the description section so that you can refer that before understanding this one. Right? So now, in order to minimization, we need to find the zero equivalence. Zero equivalence means set of final states and non-final states. So non-final states are P0 and P2, and final state is P1. And now you need to check the difference equivalence between P0 and P2. That is a one equivalence. All these things we have discussed in the previous session. Right? Now P0 on 0, P2 on 0. P0 on 1, P2 on 1. So P0 on 0, it moves to P0 itself. P2 on 0, it moves to P2 itself. So you can see both fall under the same set. P0 and P2 falls under same set, right? P0 on 1, it moves to P1. P2 on 1, it moves to P1. So here also both fall in the same set. That implies both are equal. So if you find the two equivalence also, so this is the one equivalence. Both are equal. So P0, P2 forms on the same set and P1, right? You can observe here, zero equivalence and one equivalence are same. So we need to stop the procedure, and you can simply draw the FSM finite state machine with the help of these two states. So simply you can consider P0, P2 as one state, and P1 as another state. So P1 is a final state, right? So you can observe here. So write down the table for this one. So 0, 1, P0, P1 and P2. P0 on 0, P0 on 1, P1, P1 on 0, P1 on 1, P2 on 0, P2 on 1, P1. Right? Now you can observe here P0 on 0, P0. So simply give the initial, self transition. P0 on 1, P1. So P0 on 1, it moves to P1. P1 on 0, P1. Again, P1 on 0, P1. P1 on 1, P2. P1 on 1, it moves to P2. P2 on 0, P2. P2 on 0, P2. P2 on 1, P1. P2 on 1, P1. So this is the diagram for this particular finite state machine. This is a minimization. And you can observe these two diagrams are equal. Instead of Q2, Q0, we are having the two states P0, P2. P0, P2. So that implies these two are equal. So actually this is the only procedure. Okay, this is the only procedure. Just start with the initial states, and if you find any new state, if it forms any new state, just find the transition over 0 and 1 for that particular new state and repeat the process until it doesn't form a new state. And finally, check the states of each set whether the states are non-final states or final states. And it should not be the combination of final state and a non-final state. If there is any combination between, if there is any combination of final state and a non-final state, that implies it is not equal. The two finite state machines are not equal. So if there is no combination of final and non-final states, that implies both the finite state machines are equal. So in this case, in these two diagrams, we find that all the sets are only either final states or non-final states. That means both the FSMs are equal. So I have just traced it. Okay, so I have minimized this finite state machine so that we got the same finite state machine. So that's why these both are equal. Right. So hope you understood this equivalence between the two finite state machines. So if you are having any doubt regarding this procedure, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really understood my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.